Hello, guys. Good morning. Good morning to all of you. Today, in this session, we are going to discuss vibrational spectroscopy. This is the second lecture on molecular physics, and this lecture also very important. We'll discuss a lot of things in this lecture, and you can expect a question from this, from the last lecture as well as from this lecture. You can definitely expect a question. You can definitely expect a question. So I hope audio, video, everything is all right. So we can start our session. So as I told you on the last class that rotational spectroscopy, we called it microwave spectroscopy. Okay. Now vibrational spectroscopy, this is known as IR spectroscopy or infrared spectroscopy. So vibrational spectroscopy, the vibrational level, the transition between the vibrational level falls under the infrared regime. That is why in vibrational spectroscopy is also known as infrared spectroscopy or IR spectroscopy. So something is vibrational active, it means it is IR active also. So many times different terms are used. That is why in the beginning I'm giving you all the terms. Why it is green. Before jumping into it, let's try to understand how this vibrational thing works. So rotation we have understood. This generates because of the rotation of the molecule. Rotation can happen around different axes. Let's say you have a linear molecule, then the molecule can rotate in different fashion. It can rotate in this way, okay, in this way, or it can rotate in this way. So each time you see the rotation axis is changing, and we have moment of inertia for both cases. But when it is rotating about its own axis, let's say this is a linear molecule, and if it is rotating in this way, so then there is no moment of inertia. So rotation thing you understand. Vibrational spectroscopy here, you know, molecules are made up of atoms. Atoms are connected. Now vibration means you can understand it will vibrate like this, and during the vibration, if the dipole moment changes, then it will be able to absorb electromagnetic radiation. Okay, I have just shared a post on your dedicated WhatsApp group. You can check that. That will definitely help you. So the main thing is whenever the molecule, the atoms in the molecule vibrates, there is a change in change in dipole moment, and because of that, the molecule is able to absorb electromagnetic radiation. That gives rise to this vibrational activity or IR activity, you can say. So vibrational spectra arises due to the vibration of molecules about its center of. So you can imagine it in this way. Let's say these are the vibrational level. These are the vibrational level. Now in between this vibrational level are consisting of rotational levels, small fine rotational level, you can say, imagine in this way. So these are rotational levels in between. So between two vibrational level, there exists many rotational level. You know, the separation between them is 10 to the power minus 3 electron volt, and the separation between the vibrational level we have told you it is around 10 to the power. What was the separation? I forgot. What was the separation between the vibrational level? We have given you the value, right? I think this is 0.1 electron volt, right? Good morning. Just verify this fact, the difference between the vibrational level. So let us try to understand this vibrational spectroscopy with the example of the carbon dioxide molecule. So if you have CO2 molecule, so we can imagine it in this way: oxygen double bond C double bond O. So this is the basic structure of carbon dioxide. Okay, so it has two positive charge and one negative. You can imagine it in this way. So we have dipole. Okay, now this CO2 molecule, it can have different types of vibration. Different types of vibration is possible in this case of different types of vibration is possible for CO2. First mode may be symmetric stretch. Symmetric stretch. Symmetric stretch of CO2. So you can see this stretch, this also stretch equally. If this compress equally. Able to get it? So this is the symmetric stretch of CO2. Change in electric dipole moments should be there to have IR spectroscopy or to get the molecule to be vibrational active. So for symmetric stretch of CO2, it is this change, this stretching is done simultaneously, equally. So there is no change in dipole moment, and as a result, the symmetric stretch of CO2, this mode is vibrational inactive. Means in this mode, CO2 will not be able to absorb electromagnetic radiation. I think this is clear. In this mode, the molecule is alternatively stretched and compressed. Both CO bond changes simultaneously, but the dipole moment remains 0. Thus, this particular vibration mode is, you can say, infrared inactive or vibrational inactive. In short, it is called IR inactive. Infrared inactive or IR inactive. Okay. The next one, this is symmetric stretching, this is anti-symmetric stretching. Anti-symmetric stretch of CO2. So you can imagine anti-symmetric means this is not symmetric. If you break up the literal meaning, not symmetric means if let's say this changes this amount, if I'm just showing you in this way, I'm not showing the bond, I'm just showing you in this way. Okay, here 2 plus minus. So let's say if it changes by this amount, here it is changing by this amount, here it changes this amount, here it is changing this amount. So this is not symmetric on both CO bond. So this is anti-symmetric stretch. So in this case, change in dipole moment is there. So there is a periodic alteration in the dipole moment, alteration in the dipole moment, and this vibration mode of CO2 is infrared active or IR active. Clear? Good morning, Murli. Who all are present today? Harry, Ajay, where are these people? Mouse is not working. Yes, it started working. The third one may be bending of CO2. Bending of CO2. So you can imagine maybe carbon maybe at the middle and oxygen. So they can bend in this way. So bending here, do the dipole moment change. Here the dipole moment changes periodically with the frequency, let's say new oscillation. And if there is a change in dipole moment, it will be vibrational active, right? This leads to emission of radiation of frequency new oscillation. Conversely, the molecule can attract with electromagnetic radiation and can absorb radiation of frequency new oscillation. So you can say this mode, thus this mode is vibrational active. Or IR active. Most of the time IR active is used. Good morning, Megha, Ajay. Now let's take a diatomic molecule. Let's do some mathematical treatment for this. We are considering a diatomic molecule and we'll try to find out an expression for the energy of vibrating diatomic molecule. Okay, vibrating diatomic molecule. So you can imagine it in this way, that you have an atom here and it is connected by some spring like substance, that is the bond. Okay, so this is like the bond and it is acting like spring like. So it can stretch, okay, or it can also compress. Okay, this way. So compression and stretch. So this will obey the Hooke's law. The compression and stretch means extension. Extension of a bond is like a spring, and as a result it obeys the Hooke's law. Hooke's law, F is equals to minus kx, you already know it. So in case of this, we can write the potential energy. What is the potential energy for this kind of system? You know, it is V of x is equals to half kx square. We write it. What is x? X is the internuclear separation. Now, if you feed this potential and if you put it into the Schrodinger equation, in Schrodinger equation, you know, minus h cut square by 2m d square psi by dx square plus bx of psi, bx into psi is equals to e psi. Okay. So if you plug it, you plug this potential into Schrodinger equation, that is minus h cut square by 2m d square psi by dx square plus v of x psi is equals to e psi. In this equation, if you plug, you will get a solution, right? Schrodinger equation will give solution. So solution in terms of you get eigen value and eigen vector. So solving the Schrodinger equation, we will get the energy eigen value that is given by EV, and you already know this. This is harmonic oscillator potential, right? So for harmonic oscillator potential, you get the energy eigenvalue in this way: V plus half H nu oscillation. So if you remember the harmonic oscillator potential, what eigenvalue you get? N plus half H cut omega. Actually, this is V is N and H nu can be converted into H cut omega. Okay. So here the term V, it is known as vibrational quantum number. Vibrational quantum number. Understood? So this is the energy value we get. Now if you want to express it in terms of wave number, because in atomic molecular physics we express things in wave number, means centimeter inverse or meter inverse. So wave number, to express wave number, we have to take this curly E. So what do? We divide by Hc, right? If you remember, this is equals to V plus half into nu oscillation divided by C. This nu oscillation by C is identified as omega E. So this is V plus half omega E. Where this omega E equals to nu oscillation by C. What is nu oscillation? Nu oscillation is the frequency of vibration. Frequency of vibration. And okay, I forgot to mention what is the value of V, vibrational quantum number. It can take values 0, 1, 2, 3. The way we dealt in harmonic oscillator potential, same thing is here. So our main formula is this: in terms of wave number, EV is equals to V plus half omega E. This result we get by considering the bonding between the two atoms like a spring. considering the potential purely harmonic. You see, half kx square means purely harmonic. This is purely harmonic. Later we'll see that if you add some anharmonic term, there will be some change in the energy eigenvalue. Okay. So by putting the different values of V, we can get the different values of EV. If we put let's say V is equals to 0, we get half omega E. Then we get 3 by 2 omega E, 5 by 2 omega E, and so on. So these are equispaced levels, right? Separated by omega E centimeter inverse, we can say. Thus, we have a series of equispaced discrete vibrational levels. Okay, the common separation being is omega E. You can imagine 3 by 2 omega E minus half omega E is equals to omega E. And what is the unit? As we have evaluated in terms of wave number, so the separation is omega E centimeter inverse. Don't think it is written in joule, because when you use capital EV, then it will come in joule, but when you are using curly EV, it will come in wave number. Okay, length inverse. Now here also we have, as you have told you, like if you consider V double prime, let's say V double prime means the lower state V prime plus 1, V prime plus 1. Okay, V double prime is the lower state. It is like this V double prime. I'm just showing an example. If you add 1 unit, you go to V prime. Okay, so V prime is equals to V double prime plus 1. Now let's say if you have a transition between these two levels, V prime to V double prime, so what will be the wave number change? The wave number corresponding to the transition V prime to V double prime each. So we'll express it in this in terms of new bar. New bar is this EV actually. So this is equals to new bar is what? We are talking about this transiting photon maybe. Okay. EV denotes the energy level. So V new bar, this will be E V prime minus E V double prime. So you know the value. Okay, just put it omega E into V prime plus half minus omega E V double prime plus half. Okay, so what you get, this is equals to omega E V double prime half plus 1 3 by 2 minus, let's keep it as it is. So what are you getting? This one is giving you omega E, and this will come in centimeter inverse. Okay. So we can conclude, we can say that in absorption, the vibrating molecule will absorb energy only from radiation which can coherently interact and this must be the radiation of its own oscillation frequency. So in simple term, if we say, let's say the vibrating molecule is vibrating with some frequency, right? Now you have to apply some radiation which has frequency equal to that frequency. If that matches, then absorption will happen. Okay. So kind of resonance situation is created. Now if I talk about these vibrating energy levels, if I plot, let's say, energy along y-axis and maybe internuclear distance along the x-axis, energy along y-axis and r, that is internuclear separation, so it is like we have one atom, another atom, and that is making this molecule, diatomic molecule. So as you have seen, it is giving rise to this is expressed by this harmonic oscillator potential, right? Now if I take different values of let's say V, this is V equals to 0, V equals to 1, so this will be equispaced. Okay, the separation between them will be same, so like that. This will be V is equals to 0, V is equals to 1, V is equals to 2, V is equals to 3, V is equals to 4, V is equals to 5, and so on. And correspondingly the energy for this one, it will be half omega E, this will be 3 by 2 omega E, this will be 5 by 2 omega E, this will be 7 by 2 omega E, this will be 9 by 2 omega E, and so on. Okay, the for V equals to 5, this will be 11 by 2 omega E, and so on. This so on is looking bad. Got it? Now for each case, you see the transition, the difference between them is omega E. Each time the separation is omega E. If I consider absorption, then each time we will get a line at omega E. So you will just get a single line at omega E centimeter inverse. Okay. This U-shaped curve is known as harmonic potential. Half k x square, you have already know this. The vibrational spectrum is expected to consist of single band at omega e centimeter inverse. Now the selection rule here, the selection rule between the transition between the different vibrational level, that will be same as the rotational selection rule. Here it will be delta V is equals to plus minus 1. So this is briefly the theory of this diatomic molecule. Okay, anyone has any question? Tell me. Otherwise, we'll go for a problem. Okay, if there is no question, let's go for this problem. The spacing between vibrational energy levels in carbon monoxide molecule is found to be this. Given that the reduced mass of CO is this, Planck's constant is this, 1 electron volt is this, the force constant of the bond in the CO molecule is. You have to find the K value. Can you do this? Okay, before going directly to this problem, let me just briefly tell you another thing here. Okay. So let us imagine that we have this diatomic molecule M1, M2, and this is K, spin constant K, right? Then the reduced mass for this system will be mu M1, M2 by M1 plus M2. Okay. And the oscillation will be nu 0. And the corresponding value of omega, angular frequency, root over K by mu. And nu 0 will be omega by 2 pi, that is 1 upon 2 pi root over K by mu. You can take an example like HCl is such a molecule. So this is the oscillation frequency. If you are given some potential U, then you know how to calculate the value of K. D square U, maybe U of x is given to you by dx square at maybe x is equals to x naught. This represents curvature of this potential energy curve. So these things you know. So that this particular formula you can use into this problem. Spacing between vibrational energy level is given to you. Reduced mass of the carbon monoxide molecule is given to you. Planck's constant is given to you. Force constant you have to calculate. Look, the energy is given in electron volt. means it is not talking about curly EV, it is talking about EV. So you know the formula, V plus half into H nu oscillation. Okay, use that. Spacing is given to you, spacing between the vibrational energy level. If you consider this spacing, maybe V is equals to 0, V equals to 1. You can easily calculate this spacing. What is this spacing? Obviously will be H nu oscillation, isn't it? The spacing. Spacing between vibrational energy levels, delta E, H nu oscillation. Okay, and this delta E V, let's say, it is given to you because this is equispaced energy level, right? Equispaced energy level. And what is this? H nu oscillation is equals to 8.44 into 10 to the power minus 2 electron volt. That is 8.44 happening into 10 to the power minus 2. 1 electron volt is 1.6, 10 to the power minus 19 joule. C you are getting? Very good. C will come as the answer. So if we calculate this, you will get 13.504 10 to the power minus 21 joule. Therefore, we can say H nu is omega by 2 pi, right? Omega is equals to root over k by mu. This is equals to 13.504 10 to the power minus 21. From this, the value of k you can easily calculate. So what is the value of k? Square of this 13.504 10 to the power minus 21 square into 4 pi square. Let's put the value directly. Pi to do another step. 4 pi square into mu. Mu value is given 1.14 10 to the power minus 26 divided by h square 6.626 10 to the power minus 34 whole square. So what value will you get? This will give you 186.74 Newton per meter. That is option C. If this is done, let's move on. Do this one. A diatomic molecule has vibrational states with energies EV is equals to this rotational energy with this. So this is a combination of vibrational and rotational spectroscopy. Consider the transition in which both the initial and final state are restricted to V less equals to 1 and J less equals to 2 and subject to the selection rule delta V plus minus 1, delta J plus minus 1. Then the largest allowed energy of transition is. Can you do this problem? So you can imagine it in this way, that these are the rotational energy level, right? Rotational energy level, let's say. This makes one vibrational level. Okay, this makes one vibrational level. So you can imagine it in this way, that this is V is equals to 0, this is V equals to 1, and these are like J is equals to 0, 1, 2, 3. Here also J is equals to 0, 1, 2, 3 in this way. Fatima, C you are getting. Okay, so here two types of energies are involved, rotational as well as vibrational. So both the energy values are given. So we can write the total energy, let's say E, and it is denoted by JV. J is the rotational quantum number and V is the vibrational quantum number. So we can write for the vibrational one, we can write V plus half H new oscillation. So H new is equals to H cut omega, we can write, plus it is given B times J into J plus 1. Okay, they have used small, we are using capital, okay, because we have done the theory with capital. So let's write capital, and at the end we can just put small letters. So if I just write the next energy level, maybe J plus 1, V plus 1. So this can be written as V plus 3 by 2 H cut omega plus B J plus 1 J plus 2. Okay. Now the condition of transition, you see, delta V plus minus 1 and delta J plus minus 1 for vibrational transition with delta V is equals to plus minus 1 and rotational transition rotational transition with delta J is equals to plus minus 1. Under this scenario, we get delta E, the change in the difference in two energy levels. This may be, we can say that E initial minus E final. So you can imagine that one state is denoted by rotational quantum number J and vibrational quantum number V. And the next level is denoted by the rotational quantum number J plus 1 and vibrational quantum number V plus 1. So this is the overall energy. So if you take the difference, what value will you get? You will get from the first two term, you will get h cut omega, right? And from this, you will get plus 2b times J plus 1. Are you getting this? Here, J is the lowest quantum number. Can I write it? Now, as per the question, only the transitions V less equals to 1 and J less equals to 2 is allowed. Okay, the given condition restricts us from any arbitrary transition. What are the given transition condition? Delta V, it should be less equals to 1 and delta J, it should be less equals to 2. So under this condition, if I consider that the rotational quantum number is restricted between 0 and 2. So this gives us two transitions. It may be J is equals to 0 to 1 because delta J is equals to plus minus 1. This condition also you have to keep in mind. So it may be either J equals to 0 to 1 or it may be from J is equals to 1 to 2. Okay, so this condition hold and this condition is also hold. Acha, that is why we are not getting the feeling here, not delta, it is the quantum number. Understood? So what is delta E? Largest allowed energy for transition. Largest allowed energy for transition. So you see J is the lowest quantum number. For largest, this one needs to be taken. And for the lowest one, it is J equals to 1. So delta E will be h cut omega plus 2b into 1 plus 1. So h cut omega plus 4p. That is matching with option C. Okay, understood everyone? Or any question if you have, you can ask. Anyone has any question? Ajay, Megha, Murli, understood? बताइए दोस्तों. So till now we have restricted our discussion on diatomic molecule as harmonic oscillator. Means we assume that the bonding between the molecules behaves like a perfect spring, so it vibrates harmonically. Now if the vibration, that is in case of real molecule, the vibration is not perfectly harmonic, some anharmonic term is also added. Okay, so in that case some additive term is added to the energy expression. So most Many times questions come from this also, not from purely harmonic. It may give you some anharmonic term. So diatomic molecule as an anharmonic oscillator. So it may happen that the spring is elastic. So in some real molecule, this may not be harmonic. It may be anharmonic in nature. Okay. The real molecules do not obey exactly the laws of simple harmonic motion. Okay. Real bonds however are elastic and are not so homogeneous to obey the Hooke's law. Okay. Now the actual potential contains some anharmonic term as well. Contains anharmonic terms along with the harmonic one. So previously what we had this potential half kx square. If this was the only thing, then we could have told that it is purely harmonic. Now some anharmonic term like minus gx cube plus h x to the power 4 plus some other terms. So these are your anharmonic terms. But these terms are small as compared to harmonic term. Okay. So because of this, the energy expression will also be changed. So the energy of an anharmonic oscillator may be given as, so we are writing it in terms of this EP. So V plus half. Okay. If I want to write in terms of, let's say, Carly EP. Then you can write it H. Acha, what was their expression? V plus half omega E, right? Or if I write it this omega E first, omega E V plus half. This is the from the harmonic term. This term is negative omega E chi E V plus half whole square and so on. So this one term is considered for anharmonic. This is the major term. Other terms are neglected as per this. So this, you can see, this is the maximum term. This is the next. This is the next. So on. So you can imagine this transition will give you in terms of the wave number. So here we have used this term chi e. This is called anharmonic constant. Anharmonic constant. And the fun fact is this value of chi e is much less than 1. So that is why this term, second term, is very small. Now for the previous case, the selection rule, we have seen that delta V is equals to plus minus 1. But for the anharmonic case, the selection rule is a little bit flexible. Here the selection rule contains some other terms as well. Selection rules for the transition of different levels in anharmonic oscillator is a little bit relaxed. The selection rule of vibrational transition in anharmonic oscillator is delta V is equals to, look, previously it was only plus minus 1, but now it is also possible with plus minus 2, plus minus 3, and so on. Okay. Now there are a lot of meaning here. Firstly, if I consider delta V is equals to plus minus 1, this is the intense beam. This corresponds to intense beam. This, the transitional spectrum intensity will be most intense for this case, and it gives fundamental tone. The tone level, you can call it band, fundamental band, the strongest one. For an example, let's say E transiting from V is equals to 1 to V is equals to 0. So this will be omega E times 1 minus 2 chi E. If you calculate, you will get it. Now this delta V, the other conditions like plus minus 2 or plus minus 3 and so on, this appears with decreasing intensity. Decreasing intensity, and they give something called overtones. Okay, so delta V equals to plus minus 1, this gives you fundamental band, and others plus minus 2, plus minus 3 and 1, so on, those gives overtones. So for an example, let's say EV is equals to 2 to EV 0. This will give you 2 times omega E 1 minus 3 chi E, and these all are expressed in centimeter inverse in terms of the wave number. Okay. Now special case we take. This is a fundamental band, okay. EV is equals to 1 to EV equals to 2. This is the fundamental band. Now A special case is there. V is equals to 1 to, let's say V is equals to 2. In this case, delta V is equals to plus 1, right? And if you calculate the change in energy for this case, this will give you omega E into 1 minus 4 pi E, and it will come in centimeter inverse. These are all also coming in centimeter inverse. This is very special. So this is a weak absorption. This is a weak absorption arises near the fundamental band. Fundamental band, that is V is equals to 0 to V is equals to 1. Okay. This is called hot band. This is called hot band. Why hot band is hot band? This name is given to it because it arises at very high temperature. So to have this transition, you require a very high temperature. V equals to 0 to 1, this is natural fundamental band. But if you want a transition between V equals to 1 to 2, you need high temperature. That is why it is called hot band. Okay. So let us see what kind of question you can get from this. Okay, try this problem. The expression for the second overtone frequency in the vibrational absorption spectra of a diatomic molecule in terms of harmonic frequency omega E and harmonicity constant I E is. No, hot band is only one transition. V is equals to 1 to 2. That is the only transition. For that case, that particular transition only is known as the hot band. So if I imagine in this way, let's say V is equals to 0, V is equals to 1, V is equals to 2, V is equals to 3, V is equals to 4, and so on. So V is equals to 0 to 1, this is the fundamental band. 1 to 2, this is hot band. 0 to 2, this is first overtone. 0 to 3, it is second overtone. Okay. So this figure will help you to identify. So this will corresponds to fundamental band. Zero to 1, 1 to 2, this is hot band. 0 to 2, this is first overtone, and 0 to 3, this is second overtone. Okay, D you are getting 3 omega E into 1 minus 4 XC. Have you done it before? Okay, so here the solution is quite simple. You see, EV is equals to omega E V plus half minus omega E chi E V plus half square. Other terms are neglected. second overtone, it means V is equals to 0 to V is equals to 3. So the corresponding frequency, okay, this is equals to E from V is equals to 3 to E from V is equals to EV at V equals to 0. This is equals to, if you put V is equals to 3, so 3 plus half, 7 by 2 omega E minus omega E chi E, 7 by 2 square minus omega E by 2 plus omega E chi E half square. So 7 by 2 minus omega E by 2, this is 3 by 3 omega E, and this one 7 by 2 whole square minus half whole square, so that is minus 12 omega E chi E. If you take, let's say, 3 omega E common, get 1 minus 4 chi E. That is making option D correct. चलिए आगे बढ़ते हैं. Very good, well done everybody. This one, if the leading anharmonic correction to the energy of the nth vibrational level of a diatomic molecule is this minus chi E n plus half square h cut omega. Actually, you know that, okay, in whatever form they give, you can express it in your own desired form, okay. Chi E anharmonic constant value is given to you. As I told you, this is much less than 1. You can see it is 10 to the power minus 3. Total number of energy level possible is approximately. So if I want to express it in graph, what kind of graph we can have? So this is how we expressed the energy, and here let's say we are expressing the internuclear separation. Look, when it was purely harmonic, then how did we draw the potential? We drew the potential in this way, right? This was harmonic, but as this is anharmonic, this will be little bit changed. Instead of the previous harmonic oscillator, now some anharmonic feature will come to it, and it will become like this. You can see the difference. Now, for harmonic, their separation between the different vibrational level was equal, but that is not the case in case of anharmonic. This separation is not equal, okay. It becomes continuum at some particular level. So V is equals to 0, 1, 2, and it is going up to V is equals to, let's say, V max. So if you can calculate this V max, that is the total number of energy level possible, okay. So you have to calculate this V max. So you know the expression of EV. This is purely mathematical question, you can say. Energy of an anharmonic oscillator is EV. In terms of h cut omega, it is given, so we are writing in terms of not curly, it is we are writing in terms of this, okay. So this will be V plus half h cut omega minus chi e into v plus half whole square h cut omega. Can you write it? But you can also do with curly v. The end result will remain same. Okay. You can also do it with this curly b plus half. What was that? Omega e minus chi e omega e v plus half whole square. So you have to find out the maximum value of v. What will you do to get the maximum value? What will you do? We'll take the first derivative with respect to v and equate it to 0 to get the v max, isn't it? To get v max, we can write dev by dv, and v is equals to v max. This should be equals to 0. So let's take the derivative with respect to v. So we are getting omega e minus 2 chi e omega e into v max plus half equals to 0. So 1 minus 1 is equals to 2 chi e v max plus half. So from this we can calculate the value of v max. So v max plus half equals to 1 upon 2 chi e. So v max is equals to 1 upon 2 chi e minus half. And you can see this chi e is 10 to the power minus 3. So 2 into 10 to the minus 3, if you take it to the numerator, it becomes 10 to the power plus 3, right? 10 to the power plus 3. So 1000 by 2. So 500 minus half. So approximately you can say that is 500. Okay. Is it clear? If anyone has any question, you can ask. Let us now discuss a very important thing. This one you need to understand very carefully. Okay, this is a little bit advanced, but I hope you will understand easily. vibrational, rotational spectra. So this is a mixing of vibrational and rotational spectra. Okay, fine structure of infrared branch. Okay, okay. So if we consider a molecule rotates in addition to the vibrational motion, means rotation and vibration is happening simultaneously. It can happen, na? Then total energy. As a student, we are reading rotation and vibration separately. But a rotating molecule will not wait not to vibrate. Okay, right? They are independent. They will rotate, vibrate. Okay, you can learn separately, but they will do it together. So the total energy will be the sum of the rotational energy and the vibrational energy, right? So in terms of this wave number, we can write it in this way. Okay, so hardly E total is equals to this is equals to E rotational, you know it, plus E vibrational. E rotational is B J plus 1, if you remember, plus E vibrational, considering the anharmonic oscillator, it is V plus half omega E minus omega E chi E V plus half square. So this gives a set of rotational level very small, fine. So it will be associated with the vibrational level, associated with each vibrational level. So you can imagine that inside the vibrational level we have lot of rotational levels. So let me show you this very beautiful thing. Okay, so I am just drawing the rotational level first. So these are the rotational level, let's say 1, 2, 3, 4, 5. So this may not be so evenly spaced, so their separation may be increasing, okay, because these are rotational level, not vibrational. So this is one set, this is another set. Okay, now just imagine this level corresponds to V equals to 0. These are the rotational levels corresponding to V is equals to 1. Now these are lower rotational levels. So lower on is denoted by J double prime. So let's say this J double prime is equals to 0, 1, 2, 3, 4. Let's draw another one. Let's make it 5. We don't have space. Okay, let's do it one thing. You just imagine that these are not equispaced, okay? So set your brain accordingly. Here our main purpose is to show the transitions. Okay. 5. Okay, for this one also we can make a line here maybe. So this will be denoted by J prime. 0, 1, 2, 3, 4, 5. Now let's get back to the selection rules. What does the selection rule says? We have separate selection rules for the vibrational transition and the rotational transition, right? What does the selection rules says? For the rotational one, we have the selection rule delta J, it is plus minus 1. And for vibrational, you know, we have taken an harmonic oscillator. So vibrational transition, it may be plus minus 1, it may be plus minus 2, plus minus 3, and so on. Now, if I consider the transitions, let's say these transitions from J double prime is equals to 5 to J double prime is equals to 4. What is the change? 4 minus 5 minus 1. Okay. Let's say 4 to 3 minus 1. 3 to 2 minus 1. 2 to 1 minus 1. 1 to 0. Okay. So these transitions are corresponding to delta J is equals to minus 1. Finding it convincing? Now let's say 4 to 5. What is the change? Plus 1. 3 to 4 plus 1. 2 to 3 plus 1. 1 to 2 plus 1. 0 to 1 plus 1. Will there be other transitions? Now we are just showing some dotted transitions where there is no change in J values. Okay. So it may be 0 to 0, 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. So as per the selection rule, we have these two, minus 1 and plus 1. Now these transitions gives rise to different branches. And you can see we have considered here V is equals to 0 to 1. For all these transitions, you see, we are trying to follow delta J equals to plus minus 1 and delta V is equals to plus minus 1. Okay, this one. Now, this gives rise to different branch. Okay, these are kind of branch. Delta J is equals to plus 1. This gives rise to one set of lines called R branch. If we consider delta J is equals to minus 1, this gives one set of lines called P branch. And finally, delta J is equals to 0, which we have shown in the dotted line. This gives one set of lines called Q branch. So for this delta J is equals to 0, which is of no importance for us, we can just represent it by this dotted line. And symmetrically around this, we have P and Q branch, so P and R branch symmetrically. So if I say that this corresponds to delta J is equals to 0, and this separation is 4p. This will be plus 1 means R branch. So this is R0, this line is R0, this branch is R1, R2, R3, and in this way. And on the other side it is P0, P1, P2, P3. So for these cases, we have delta J is equals to plus 1. This corresponds to R branch. And these lines corresponds to delta J is equals to minus 1. This corresponds to, अच्छा हम लोगों का जगह नहीं मिल रहा है दोस्तों, जगह नहीं मिल रहा है. Yes, बच जाएगा. So this corresponds to P branch. आप लोगों के कॉपी में तो जगह होगा, राइट देम. So if you get confused with this PQR, you can imagine it in this way. What is the lowest number? Minus 1. So delta J is equals to minus 1. This corresponds to P branch. P, Q, R. Delta J 0. Q branch. Delta J is equals to plus 1. In this way you can remember. Minus 1, 0, plus 1, PQR. Okay, is it understood, guys? Tell me. If anyone has any question, you can ask. No one has any question? Look, we solved this problem. Yeah, this one. We have told you that this V is getting a maximum value. So this is the maximum energy, you can say. After this, the molecule will be dissociated. Molecule will be broken up. It will get dissociated. Okay. At this particular value, the dissociation will happen. Okay. This is the V max. So if you put this value back into this expression of energy, that is the energy corresponding to the dissociation energy of the molecules. I hope this is very straightforward. At least after I said yes. Okay, this problem we have already done. Okay, already done. By mistake I have added this. Anyways, do this problem. Okay, similar problem here. It is a little bit modified. It is one step ahead. The energy required to dissociate the molecule. So what you gonna do? You're gonna find out the Vmax and you will put the value of Vmax into the expression of the energy. Okay, do it. I'll be back. Nikal ja. Do it quickly. Okay, so we are directly using the result from our previous problems. We got previously Vmax. I am not showing the calculation again because we have already shown you the calculation. We are starting from here. So we got how much? 1 by 2 chi e minus half. This one we got, right? So that is approximately, since chi e is very much small, so we can approximate it as 2 chi e. That's because chi is much less than 1. Can I do it? So this makes our task easy. So we can say that EV, the maximum value, it is corresponding to this one, okay. This is corresponding to Emax, this value Emax, this is corresponding to Vmax. Option A everyone is getting, but option A is not the correct option. Let's see whether we get option A or option C. EV max is equals to how much? Acha, even if we don't approximate, if I approximate this result, then that is creating a more problem. If we don't approximate, then I think it will be more, it will be easier for us, because that half factor will then be vanished. Okay, so h cut omega 1 upon 2 chi e minus chi e times h cut omega times v plus up, so 1 by 2 chi e square, and that gives you h cut omega by 2 chi e 1 minus half, something like this. Okay, 1 minus half, and that is equals to h cut omega by 2 chi e and half, so 4 chi e. Chanda C, yes, C is the answer. The EV max we have got. If I calculate the 0 point energy corresponding to V is equals to 0. Look, for harmonic one, h cut omega by 2, and this one chi e h cut omega by 4. Therefore, look, dissociation means you have to give this much of energy, right? E0 EV max. The dissociation energy is E dissociation is equals to E max minus E0, because you are not starting from 0, you are starting from E0, right? Because the 0 point energy is not 0. H cut omega by 4 omega would have been the answer if the 0 point energy was 0, but 0 point energy is not 0, you know it very well. So we have to do it in this way. H cut omega by 4 chi e minus h cut omega by 2 minus plus chi e h cut omega by 4. If we take h cut omega by 4 chi e common, you get 1 minus 2 chi e plus chi e. Is it clear, guys, why C is the answer, not A? Because this is harmonic oscillator, and for harmonic oscillator 0 point energy is not 0. How do you get this E0? By putting V is equals to 0 in this expression. Write down, guys, if it is clear or not. Then we'll proceed. चलिए आगे बढ़ते हैं. Let's go for Born-Oppenheimer approximation. Born-Oppenheimer, इस नाम से एक मूवी आया है ना अभी, Born-Oppenheimer approximation. Oppenheimer by Christopher Nolan. So we can write the total energy as a sum of, we have rotation, we have vibration. Another term you have, can you tell me? In the total energy, we have the contribution from rotational energy, from vibrational energy. Another contribution is there. Can you tell me what is that? That is electronic. So as per this Born-Oppenheimer approximation, which implies that the rotational, vibrational and electronic energies are energies of a molecule are completely independent of each other. This is given the name of Born-Oppenheimer approximation. In terms of wave number, if you write delta E total, delta E rotational, delta E vibrational, delta E electronic, it is in centimeter inverse. And you know the approximate order of their magnitude. Approximate orders of magnitudes of these changes means it is the separation between the different levels. Okay, delta, when we are using delta, means it shows the separation, delta nu bar, you can say. So which one is greater? Delta electronic, that is the greatest, right? How much greater it is? It is approximately 10 to the power 3 times, 1000 times of the vibrational one, approximately. And you know the vibrational is approximately 100 or 1000 times. We can imagine 10 to the power 6 times the rotational one. So this is known as Born-Oppenheimer approximation. Okay, let's quickly go to the another principle called Frank-Condon principle. This is the last topic, I think, for today. Frank-Condon principle. What is this Frank-Condon principle? It states that, okay, now you imagine in this way what we had. If I take the case of maybe harmonic oscillator case, we had previously this is a harmonic oscillator potential, okay, and the energy levels you can see it was given in this way. Okay, these are what vibrational level, and in between what we have rotational level, this fine rotational level in this way. Try to understand, these big lines are vibrational, the small lines are showing rotational. What about electronic? Electronic will be something like this, control C, control V. Okay, so this is like one electronic level, this is another electronic level. The transition between electronic level means the fine structures between of the vibrational levels. The transition will be happening like this. Okay, this is one electronic level, this is another electronic level. Now you understand. Smallest, finest, these lines shows the rotational energy levels. These big lines shows the vibrational energy levels, and this is a whole makes an electronic level. This is a whole makes an electronic level. Now transition between electronic level means transition from this to this, this to this, this to this. Look, in most of the cases we are considering absorption, right? You are hitting something, so absorbing, the molecule is absorbing energy. That is why every time we are showing in this way, the transition we are showing upward transition, we are not showing downward transition, because every time the molecule is getting energy from outside. So if it is getting energy from outside, it means it is absorbing, right? That is why always we are showing vertical upward transitions. So it states that an electronic transition, now we have understood what does electronic transition mean here, means from this to this, this to this. So it states that an electronic transition takes place so rapidly that there is no change in the internuclear distance of a vibrating molecule appreciably during the transition. What does it mean? It means that, let's say, it starts from one particular phi. Okay, now the transition is so rapid that this value of V does not change in the transition. In molecules, the individual atoms the individual atoms vibrate about their mean position, right? And the internuclear distance changes continuously. You can easily understand it. If you think of two atoms which is making a molecule, so if I say that they are vibrating, so they are vibrating about their mean positions. So let's say at one instant, this is the internuclear separation. Now maybe it is expanding, goes to this point. At that particular time, the internuclear separation is changing. So that is what it is talking about. So they vibrate about their mean position, and as a result of that, the internuclear separation or internuclear distance change continuously. Okay. So Frank-Condon principle, this can be restated. Frank-Condon principle can be restated as, so same thing we are considering in a in some other wording or other sentence, that transition between electronic states occur vertically, okay, in a potential energy diagram. So this one is more important. Transition between electronic states occur vertically in a potential energy diagram. So let us consider few examples. Okay, this one is a little bit odd, but that's okay. We are considering a potential energy diagram. Maybe we can consider it here or here or here. Yes, let's consider it here. So in the potential energy diagram, what remains along the y-axis? You know it very well, that is energy. And along this we have the internuclear separation R. Okay, internuclear separation R. This particular case we are considering, this is the absorption spectrum of O2. O2, oxygen, absorption band. One question came based on this. Okay, that is why we are turning that question into a theory. So we have to show the transition between two electronic states. So let's say one electronic state is here, okay, like this. Another electronic state is here. So we have these vibrational levels embedded, and here also we have the vibrational levels. Lower one means you will denote it by double prime. So let's say V double prime is equals to 0, it is 1, 2, 3, and here these are the upper one, so it will be denoted by V prime, 0, 1, 2. The way we did for rotational, here we are dealing with vibrational. Okay, so let's say V double prime of 0 here. So you can imagine what is the internuclear distance. The R value is here. Now this transition is happening from V double prime equals to 0 to V prime is equals to 0. So you can see this is vertically, this transition is vertical transition, and you see during this transition the R value is not changing, internuclear distance is not changing. That is what is said in the Frank-Condon principle. So in this figure, let's say this is figure A. So let's try to explain this figure A. This vibrational potential curve, this is known as Morse curve. Okay, the vibrational potential energy curve called the Morse curve has no relative displacement along R. So you can see same R value for two electronic state transition, two electronic states. Okay, the vertical transition being the most probable transition, most probable transition. The strongest line would be, you see, from 0 to 0, this transition will be strongest one, 0 to 0. The chances of other transitions are also there. The chances of other transitions being much less than this 0-0 transition. So let's say maybe 1 to 0 or 2 to 0, these transitions are, the chance of these transitions are very less. So these lines rapidly diminish in intensity, rapidly diminish in intensity. So if I just represent this thing which you have just explained in a figure, it would look like in this way, that this is the strongest line for 0-0 transition, and as you go for other transitions, this diminishes appreciably. Okay, so it is like 0-0, like 0-1, 0-2, 0-3, and so on. Is it clear? Now let's imagine this second scenario. Let's say we'll call it figure B. Figure B, oh my god. This is little bit difficult, let me tell you guys, but I'm trying to make it simple as possible for you. So just try to understand, okay? Don't give up. Now we are considering a situation in this way. In this case, 0 to 0 was there, okay, in the last case. Now we are considering a scenario in such a way that is like this. Okay. So if you get a scenario like this, vertical transition is the main. So in the second figure, what you observe? So here in figure B, the two potential curves shows potential curve, the electronic states. The electronic states show appreciable relative displacement along R. As you can see in the first image, there was no separation between the internuclear distance, but here you can see there is an appreciable shift in the internuclear distance along R. So vertical transition is possible for vertical transitions for V double prime equals to 0 level to V prime equals to 1 is most likely to occur. Okay, you can see the vertical one is most likely to occur between V double prime equals to 0 to V double prime equals to 1. Most likely to occur. Okay. Other transitions are also possible, but those are less likely. Transitions to lower means nu prime equals to V prime is equals to 0, lower, and higher V prime states being less likely. Okay, being less likely. So the intensity, which intensity will be maximum? The vertical one. So the intensity of 0 to 1 is maximum. Okay, of 0 to 1 is maximum. So what kind of spectrum you will observe for this case? Hmm? 0 1 is maximum. So this will be 0 1, and if you go higher or lower than that, the intensity will be diminished. Okay, so this corresponds to this. This is actually carbon monoxide. Okay, carbon monoxide molecule. This phenomena is observed in carbon monoxide molecule absorption band. First one is O2 molecule, and this is observed in carbon monoxide molecule. Okay. Now a third case is there for I2 molecule, iodine. Okay, figure 3. Figure C, iodine. In this case, what we have in the electronic states, we have continuum. This iodine case is little bit slightly different. Okay, let's do the third case here. The case of iodine. This is observed in the case of I2 molecule. We have new double prime is equals to 0, 1, 2, 3 and so on. Here we have new prime 0, 1, 2, 3 and so on. So for this case of iodine, we get the spectrum like this. Firstly, we will get discrete lines like this, discrete lines like this, and it will become continuum later on. Like this. Continuum means it is showing the dissociation. Now the explanation is written here. The continuum in the molecular absorption spectrum represents the point at which the energy of the absorbed photon is sufficient to dissociate the molecule. So you can see it starts dissociating after some particular value. Now previously we get discrete line, now you get continuum. Continuum means it shows the dissociation. At this stage, the vibrational levels of the excited electronic state, this is the excited electronic state, and you can see this is no longer discrete but it is continuum. And no longer discrete because the molecule is no longer bound. Instead of transitioning to another bound vibrational level, molecules bond breaks and the atom or fragments move apart indefinitely. So don't worry about this. This is you can just have a go, have a just give it a read. Okay, don't worry too much about it. It's like very advanced level thing, and we have covered it yet. And with this vibrational spectroscopy is over. In the next class, we'll be dealing with Raman spectroscopy. Okay. If anyone has any question, you can ask. Otherwise, we'll end the session. It's a quite long session, but we have successfully completed IR spectroscopy. Okay, and we have also considered the combination of IR and microwave spectroscopy. Okay. If there is no question, let's end the session here. Thank you guys. Thank you very much for joining the session. Like this stream if you like it. Bye bye. Take care. Have a great day. चलिए मिलते हैं नेक्स्ट क्लास में मंडे को. दिस इज सैटरडे. Enjoy the weekend. And okay, Sunday test, the next two units we have taken up to, I think, quantum mechanics, right? So the next 2 units are thermal statistical and electronics. So those 2 units will be in the Sunday test. Okay, those who have not enrolled for Sunday test, you can enroll from the website. Chalo, bye bye, take care.